Now, Huffman code, the problem that we had is we were storing all the patterns in the dictionary, and as a result we have to assign codes for even for very less frequently occurring patterns, like you see this pattern S12. So, S12 is occurring only once, and when it is occurring we are sending a code which is 6 bit wide, whereas the original pattern is only 4 bit wide. So, we are losing a lot. So, the selective Huffman coding, what it does is that it does not put all the patterns onto dictionary. It only puts the patterns which are occurring very frequently onto the dictionary. For the remaining patterns, so it will not put into the dictionary. So, what happens is that while I am doing this transmission from ATE to the decoder, ATE to the decompressor, when I am doing this transfer, the first bit that is transferred, so that identifies whether it is a dictionary pattern or a normal pattern. So, if the first bit that is transferred is a 1, if that is 1, that means in the next I am going to transfer some code, some coded pattern, and if this bit is 0, in that case it means that the next bits that I am transferring is not a pattern, not a code, but it is the actual pattern. So, if we do like this, then for the patterns where we see that the coding is not going to be helpful, so we can transfer them directly to the decoder. So, decoder will simply bypass the dictionary, and whatever pattern is coming, so it will put it onto the output. So, that it can do. So, on the so decoder, the way it works is that it checks whether the bit is 1 or not, bit is 1 equal to 1 or not. If it is equal to 1, in that case it will consult the dictionary, and from the dictionary it will get the pattern, and that will be applied. Whereas, if the bit is 0, then it will not consult the dictionary, it will take successive bits, and it will just pass those successive bits to the output, so to be applied to the circuit. So, here I have got the circuit under test. Okay. So, this will be the decoder will be working like this. So, that way we can save a lot, like in this case you see that S0, S1 and S2. So, maybe we have decided that we will store only 3 patterns in the dictionary, S0, S1 and S2. So, for them the code that is assigned is 10, 110 and 111, whereas for the remaining patterns, so we decide that okay, we will not keep them in the dictionary. So, for them the most significant bit is 0, and the remaining bits are same as the pattern that we have. Okay. So, it is 0111, here also it is 0111. So, it goes like this. So, the advantage that we get is that this tree that we have at the decoder, so it is much simpler. So, now you see we have decided to keep only S0, S1 and S2 in the dictionary. So, while constructing the Huffman tree, at the first level we combine this S1 and S2, and this is occurring 13 times, this is occurring 7 times. So, when we combine them, so we get a node that has got 20 occurrence, and with that this S0 will be combined. So, we get the 42 occurrence node at the top. Now, the code of S0 is given by 0, and so only 1 bit coding is sufficient for S0. Similarly, so previously S0 was requiring 2 bit coding, you see 1 and 0, now it is requiring only 1 bit coding. Of course, 1 extra bit is needed, which is identifying it that it is a code, not the pattern. So, that is there. Similarly, for this 13 for S1 and S2, so the number of bits needed is equal to 2. Of course, again the same thing, that 1 extra bit is needed to identify that it is from the it is a directly a pattern, it is a code to be consulted with the dictionary, and not a pattern directly. So, this is the advantage of this selective Huffman code. So, in selective Huffman code, so it can give rise to further compression compared to the normal Huffman code, and the second advantage is that the dictionary size can be drastically reduced. So, the designer can do a trade off, like if you think that okay, I do not want to give much of effort on the much of area for this for holding the dictionary, then the dictionary size can be reduced, and and the dictionary will be able to accommodate only first few most frequently occurring patterns, but the compression will suffer, but at the same time that may not be that high, because the most frequently occurring patterns are definitely covered by the coding. Next, we look into another strategy which is known as run length coding. So, run length coding is like this. So, it first of all it sees what is the size of the runs of zeros. Like if you see a test pattern, so if it is a test pattern is say 1 0 0 0 1 0 0 0 0 1 0 like this. Now you see that at this part I am transmitting 5 zeros, at this part I am transmitting 4 zeros. So instead of doing this, I can say that initially I have got, say there are 2 zeros here. So initially I have got a run of 2 zeros, then I have got a run of 1 0, then I have got a run of 6 zeros, and then I have got a run of 4 zeros. So this whole thing can be represented like this. So if we just tell for how many what is the run of zeros that we are seeing while doing this transfer, then we can say that okay, we can transfer those many bits only, what is the run length of that thing. So this is like this. So this is so this first of all we identify the symbols that can be. So this single one, that is no zero is there, so that is one case. Then there is a single 0 followed by 1, 2 0 followed by 1, 3 0 followed by 1. Ultimately we have got 6 0. So that is the maximum, say. So this is this is there. So what is done? This the symbol 1 is coded with 3 0, the code word is 3 0. The 0 run of 1 is coded as 0 0 1, run of 2 is coded as 0 1 0. So till this much we see that we are either transmitting more number of bits in the code word, or we are transmitting the same number of bits as the code word. But from that point onwards, you see that this is not going to be same. Okay, so this is going to be 0 0 4 bits. Instead of sending 4 bits, we are sending 3 bits. So what the decoder can see at the decompressor can see is that it just checks the line coming from the ATE. So if it finds next 3 bits as 0 0 0, it will know that the actual symbol is 1. If it finds that the next 3 bits are 1 0 0, it knows that in the scan chain I have to put in this particular pattern 0 0 0 0 1. So that is to be put in. So at the decompressor end, so we can recompute the test pattern given the code word information. So if the code word that is in the dictionary, in the ATE we are storing the code words, and instead of storing large runs of zeros, so we are storing the corresponding codes only. That code is getting transferred to the decoder, and the decoder is in turn computing back the original symbol. Now what happens is that many a times, so while testing the pattern, so while shifting the pattern, so we see that the pattern is going to be same. Like say this is the in this case, say this is the scan chain. So in the scan chain we already have some pattern. Now the bit that we are going to shift, if it is same as the previous pattern that is shifted out, then I can say that this is this result is if this bit is 0, then what will happen? The same bit that is coming here will be coming at this point, so it will be shifted here. So if these two, the next bit to be shifted is same as the last bit here, then I can shift in a 0. So from the ATE actually this input is coming. So if I have got more number of zeros here, then the coding will be more efficient. So if we have the scan chain structure slightly modified, so that the ATE input, instead of feeding this scan chain directly, if it feeds this XOR gate, and this scan chain bits are the bit that is scanned out from the scan chain, so it is XORed with the next input bit, then it is very much possible that we have got large number of zeros generated in the sequence that has to be fed here, because the bits may be same, and that happens due to the correlation between the test patterns, and there are don't cares in the test pattern. So don't cares can be filled up, so that we can get more similar type of test pattern, so that these zeros will occur more frequently. So the bits will be same. As a result, I can feed a 0 here. So, this run length code is a variable to fixed length code. By modifying the scan chains architecture slightly, we can increase the number of zeros that we have to shift into this from the ATE. So, decoder can the compression mechanism can take help of that information. So, instead of storing the test pattern, so we are actually storing the difference, and if the difference is having more number of zeros, which is very much likely, then we can we may shift in less number of so we may have to shift in less number of bits, because long runs of zeros can be found. Another code based scheme is known as Golomb code. So, it is a variable to variable length coding. So, here we have got these groups like A1 group. So, A1 group, so what is done is the original pattern, say original run lengths that we have. So, it is divided into groups of equal sizes. So, A1, the group A1, so it has got the run lengths 0, 1, 2 and 3. Group A2, it has got run lengths 4, 5, 6 and 7. A3 has got 8, 9, 10, 11. So, like that. So, run lengths are grouped into equal sized partitions, you can say. Then for each group we have a group prefix. For group A1, the group prefix is 0. For group A2, the group prefix is 10. For A3, it is 110. Now, individual run lengths within a group, so they are coded with the individual tail patterns. Like say there are four run lengths in each group, so they are to be coded as 0, 0, 0, 1, 10 and 1, 1. So, the run length of 0 is finally coded as group prefix followed by the tail. So, 0, 0, 0. Similarly, run length of 1 will be coded as 0, 0, 1. Run length of 3 is coded as 0 and then tail is 1, 1. So, 0, 1, 1. So, when you go for larger run lengths, you see there are lots of saving. Like when I have got a run length of 11, you see the group prefix is 110 and tail is 11. So, these 5 bits are sufficient for sending the thing. So, this way when we are having when the run lengths are small, then the group prefix is also small. So, that way it is saving the bits in the group prefix, and the tail part is of course same for all the cases. So, group prefix part, so if a pattern is occurring, if you get a longer run length, then this will lead to saving. So, this is a typical example, like say this one is Golomb code variable to variable. So, this is the test pattern that we have. Now, you see this is a run length of 2, this is a run length of 4, this is run length of 3, this is 4, again 4. Okay. So, like that we have. Now, if we just do the corresponding coding, so this is run length of 2. So, run length of 2 is coded as 0, 1, 0. So, you see in the instead of sending 0, 0, 1, we are sending 0, 1, 0. Then I have got run length of 4. So, run length of 4 is coded as 1, 0, 0, 0. So, these instead of sending these 5 bits, we are sending 1, 0, 0, 0. Similarly, this one this is a run length 3. So, that is again coded as 0, 1, 1. So, by consulting this table, so we can see that we can get the corresponding code words from this table, and those code words will be used here for coding. Okay. So, this original TD, so it had 43 bits. So, when we do this encoding, so this comes down to 32 bits. Now, this is a very common situation, and in fact, we can do many more modifications to the test pattern set. As we have already seen that the test patterns will have large number of don't cares. So, these don't cares can be filled with 0, so that we can have we can say that okay, we will get the Golomb code will be benefited, because it will find more number of more larger run lengths of zeros. And sometimes there is another modification where we consider both run length and 0 and 1. So, there has to be another bit which will be doing this complement from 0 to 1. So, it tells whether it is a run of zeros or run of ones, and then the run length. So, if that is done, then also there will be saving when we are looking into the coding. So, this dictionary based coding techniques, the main problem that we have is that we have got this dictionary to be maintained, and this dictionary size is an issue, and many a time what happens is that this dictionary is not we cannot keep this dictionary to be very large. As a result, compression ratio may not be very good. So, next we will look into linear decompression based schemes, and under that category we will look into several subcategories. So, what do we mean by linear decompression based scheme is that, say this is a structure. Okay. So, let us say that this is a structure where we have got some flip flops and some XOR gate. This is a shift register, and in between we have got this XORs. Okay. Now, if this initially, if these cells initially have got x1, x2, x3 and x4 as its inputs, and we have got this x5, x6, x7, x8. So, they are fed as input to these XOR gates in successive cycles. Then what will happen? So, if this machine is made to operate, then what is Z9? So, Z9 is nothing but this. So, this say let us say what is say Z4. So, Z4 we have to start with this one, because first we will get Z4. So, Z4 is x1 XOR x6. Why? Because this this x1 is coming to this XOR gate and this x6 is coming to this XOR gate. So, as a result, this Z4 is going to be equal to x1 XOR x6. Now, what is Z3? Z3 is nothing but this x1 XOR x4, because Z3 is getting this x1 from here and it is getting x4 from here. So, these two values are XOR to get Z3. So, similarly, this Z1, so Z1 is nothing but this x2 XORed with x5. So, this x5, x7, x9, so they are actually fed in sequence. So, initially these values x1, x2, x3, x4 are loaded into these cells, into these flip flops, and then this x5 is fed, x5 and x6 is fed in the first cycle. So, they are added by these adders by these XOR gates, and accordingly this Z1, Z2, Z3, Z4, these outputs are computed. Then after one cycle, what will happen? This x7 will come here, x8 will come here. So, accordingly this Z5, Z6, Z7, Z8, so they will get computed. So, but by this time there has been some shifts. Okay. So, if we explore properly, it can be seen that Z5 is nothing but x3 XOR x7, because x3 will come here, x3 will get shifted to up to this point. So, of course, there are many more things, but after doing the simplification, it can be found that this Z5 is x3 XOR x7. So, what is happening is that, you see, ultimately we have got this pattern Z consisting of Z1 to Z12. So, Z1 to Z12. So, 12 bit pattern we are getting here, and for that purpose we have stored this part is x1 to x10 into we have to apply this x1 to x10 to this machine to get the values Z1 to Z12. Okay. So, if Z1 to Z12 happens to be my test pattern, if Z1 to Z12 happens to be my test pattern, and I have this machine available, then I need to store this x1 to x10 only as the input to this machine. So, input to this machine is, so I can consider this whole thing as if I have a machine here where the input is 10 bit input consisting of x1 to x10, and as an output it can generate Z1 to Z12. So, 12 bit output it can generate. So, if this happens to be my test pattern, so I do not need to store 12 bits in the ATE, but I need to store only this 10 bits. So, this 10 bits can be given to the machine, and the machine, that decompressor, so decompressor will generate the 12 bit patterns, and every if my ATE has got 2 channels, then in the 2 channels, so I am sending this x5, x7, x9 and x6, x8, x10 serially, and this machine, it is generating this test pattern. So, so if it has got 4 scan chains, for example, then these individual scan chains are being fed by these 4 lines. So, this is the basic idea of the linear decompression strategy. So, we have got a linear machine which performs the decompression, and it helps it's all the operations that it does is linear operation. You see that ultimately z's that we have got, so they are nothing but linear combination of these x values. So given this machine, so can we find a set of x values that can give rise to this to the z value. So that is the main question that we have. So if you just so this whole operation can be represented by this particular matrix. So you see that in this case, after doing this analysis, so we have found z1 to be equal to x2 xor x5. So you see that here this matrix, this x2 and x5, so these two bits are 1, so rest are all 0. So when you do a multiplication, so x2 xor x5 becomes equal to z1. Similarly, x3 becomes equal to z2. So if you look into this, z2 equal to x3, so in the that is represented by this matrix. So whatever computation we have seen here, so it can be represented by this matrix, and by simple matrix multiplication we can get the test pattern. Okay. So if there are large number of don't cares, then of course we don't have to this matrix can be made simple. So we don't have to have large number of rows. So that way we can save. So how does it work? Suppose my z is equal to this one. So this is my test pattern 1. Then these two bits are don't care. Then I have got 0 1 1. Again all these bits are don't care, and this is a 0 bit. So this is the test pattern set given by the ATPG. Okay. Now for this don't cares, I really do not bother. So whatever this decompressor generates, I don't bother about it, but the decompressor must generate these bits, the care bits properly. Okay. So it must generate these bits properly. So how to do this thing? So we just augment this with the output column 1 0 0 1 0 1 1 0, and then do a Gaussian elimination. So when do we Gaussian elimination? So we find that this x may be set equal to 0 1 1 0, this particular pattern, so that it will be giving us this solution. Whereas in this particular case, so z is this, but here the Gaussian elimination cannot give any solution. So that way it is so this particular pattern cannot be generated by this machine. And why it has not been able to generate? Because you see that two rows have been become same. So the Gaussian elimination will convert it. This will be all 0. So it will be not be able to do the solution finding. So this Gaussian elimination cannot find this. So whatever it may be Gaussian elimination, maybe some other technique, but ultimately what we want is that this these x values are to be, we have to find these x values so that these care bits can be generated. So if we can do that, then we are then we can say that okay, we can generate the test pattern using these x values. So what works finally is that the combinational linear decompressor. So from the XOR network, so is there, and this XOR network will feed the scan chains, and this scan chain output will be coming. So again the scan out bits, they will be coming to the MISR. So MISR will do the analysis, and then the response will be put onto the output. So this is the combinational linear decompressor. Okay. So this input is coming here from the ATE, and this XOR network is doing the operation. Okay. So we will continue in the next class.